Hi, everyone. Now, I want to talk to you about removing discontinuities. And the only time we can talk about removing discontinuities is when we have removable discontinuities like points. We can't remove a discontinuity that is infinite, like a vertical asymptote, and we can't remove discontinuities that happen like jump discontinuities. And the only two functions that we really need to worry about are rational functions and piecewise functions. So rational functions, we can have something like this. So if I gave you an example that's saying, you know what, f of x is equal to x squared minus 25 all over x plus 5. Now we talked about this function before actually, and we said that if I were to, factor that top, then I'd have x minus 5, x plus 5, all over x plus 5. Now we can see that over here, I can cancel out this x plus 5 with this x plus 5. Then we're left with x minus 5, right? Now, then we're saying, okay, so our discontinuity is happening over here when x is equal to negative 5, right? So then what if I said, let's take this negative 5 and actually sub it in. Let's see what the function is going to be at this discontinuity. So if after we've kind of removed this discontinuity. So we're going to say, all right, well, let's try then to say we have negative 5, negative 5, then we have negative 10, right? So then we're saying, okay, well, look at this. We have this function at this discontinuity. Once we've removed the discontinuity, we're saying that then at x is equal to negative 5, our discontinuity, our function, once it's removed, once we've kind of removed that common factor, once we've removed the x plus 5 and x plus 5, we end up getting that the function is equal to negative 10. So we can rewrite this as a piecewise function. We can rewrite it and say, you know what? Let's write our f of x and break it down into the two intervals where first I had my function x squared minus 25 all over x plus 5. And this existed everywhere, right? Except when x is equal to negative 5, because we know that that would make it undefined. So then this exists where everywhere except when x is equal to negative 5, right? And then we said that we have also the function is equal to negative 10, and this is when x, oh, sorry, I forgot to say, when it's not equal to negative 5, and this is only when x is equal to negative 5. So then our function can be broken down into two intervals. Now the intervals are really just saying for everything and then for 1 point, right? Because this is a point discontinuity. So then we're saying, okay, so the function, once I kind of got rid of this, this removable discontinuity, the function exists at 10, at x is equal to negative 5, and it's equal to 10. So then we're looking at this, and actually I've made this into a continuous function, right? Because over here, everywhere f of x exists, and we can see that the limit is equal as well, because this removable discontinuity, when I plugged it in, we got negative 10. So we can see that our function is actually continuous everywhere in its domain, right? Okay, now let's look at piecewise functions. So we talked about how, we're going to have rational functions. So here we were looking at rational functions. Now let's look at piecewise functions, because the other type of question that you can get is when you have a piecewise function. Actually, let me pull that down a little bit. All right, So the other situation is where you'll have a piecewise function, and you know what? You're going to be asked something like this. So you can be asked something where it says, you know what, f of x is this piecewise function that is existing as x plus 3 in the interval where x is less than or equal to 4, sorry, less than 4, and it is kx squared when x is greater than or equal to 4. Okay. All right. So here's what you're going to be asked. You're going to be asked, you know what, find the find a k value that would make this function continuous. And what you need to do is you need to make sure that, you know what, if it's a continuous function, then at that point, they should be equal, right? Because we said that the function, if it's continuous, then the limit is also the same, whatever, if if I'm going, the limit exists. So if I'm coming from the left hand side or the right hand side, then I then the function exists, then the limit exists at that point. So if I'm saying, does the function exist, and I want to call this over here, I want to call this point where the function's kind of where it breaks. So it initially it's all equal to this, and then at 4, once it starts becoming greater than 4 or equal to 4, it starts becoming this over here, kx squared. So I want to call this the break point. And at this break point, this is the point in question. We're saying at this point, x is equal to 4, are we getting a continuous function f of x? So then we're saying, just like we said earlier, that in order to check for that, we know that because the limit has to equal the same from the right-hand side and the left-hand side, then we can just set them equal. We can set these two functions. And remember, the limit also has to equal to the value of the function, right? From the previous sections, we talked about the conditions, the 3 conditions. So remember, the first one, the function has to exist at this point, which for us is x is equal to 4. The limit as x approaches 4 has to exist, but not only exist, it has to equal to the function at x is equal to 4. That's why we can set them equal in order to kind of assume that they are continuous, because it's asking us what is the value of k that will make this continuous. So we're assuming it is continuous and there is a k value that makes this possible. And we're trying to find this k value. So we're going to set them equal and basically isolate for k. So then we're going to say, okay, well, I'm just solving for k. So we're just going to divide everything over here by x squared. So divide by x squared, divide by x squared. So then we're going to just have k is equal to, actually, why don't we write this as 1 over x plus 3 over x squared. And remember, we're saying this is at x is equal to 4. So we're going to sub that in. We're going to say k is equal to 1 over 4 plus 3 over 16. Okay, and I can simplify this further. I can say then k is equal to multiply by 4, multiply by 4, 7 all over 16. And this is the k value that would make this function continuous at x is equal to 4, and therefore continuous everywhere else, right? Okay. All right, I hope that helped you. These are the 2 common questions for this section. These are the 2 common kind of approaches where you're going to make a removable function continuous by removing the discontinuity and making it into a piecewise, or you have a piecewise function and you're trying to make it continuous by finding a k value that makes that possible. It could be k, it could be other variables. So I hope that helped, and I hope I'll see you in the next videos where we're going to do more questions and look at more topics. Bye.